All right, so we're looking at chapter test from the homework, chapter review from homework, and we're also going to look at 6.9 here. So we're going to start out with the chapter test homework number 7. So in this one, we just want to describe the end behavior of the graph of the polynomial function, and then we want to evaluate the function for certain points. So here we're looking at -4, -3, -2, all the way up through 4, and then graph the function. So I'm going to kind of outline how to do this problem. I don't know that I'll do every single step here, or I may just kind of skip through as we go through each of these points in terms of evaluating. I won't write each of them out, but I will explain how to kind of go about this. The first thing that I want to concern myself with is whether this thing is positive or negative. So I want to look at my leading coefficient. My leading coefficient here is negative. So since I have x to the third, this is my highest degree, this is my leading term, I get a -3 here. Now, cool if it's a 3, if it was 1/3, cool as well, but I don't really care. Really just care positive or negative. The next thing I would really like to look at is the degree of the function. So when I'm looking at the degree of this thing, it's the highest degree of the x, which in this case is 3. So this is a degree 3, and the thing that I care about is that it is odd. So here I have an odd negative function. So I want to know at a high level what odd negative functions look like. Odd negative functions look like this. Then I go up to the left, down to the right, oops, there we go. And then they may do some crazy stuff in between. That's basically all I care about. So in terms of where these things are going to cross, that's where we get our factoring and that's where we get our zeros. So let's look at this function here. So again, I'm talking more about the things that I'm concerned with than the actual problem itself. So if I had something that looks like this, here's my y equals -3x to the third minus 6x squared. I'd see I have a -3 here, a -6 here, and I have x to the third, x squared. So I'm going to factor out a -3x squared, and I'm going to see what's left. I would just have x plus 2. So now I've got y equals this chunk times this chunk. And I'm going to set each of those chunks equal to 0. The first one, -3x squared equal to 0, will give me x equals 0. The next one, x plus 2 equals 0, will give me x is -2. Now these are my two zeros. So in my graph, instead of just doing the crazy high level thing, the thing that I'd be looking at now is that I've got one which is going to cross, I'll do it like this. At 0, I'm going to have a point there, and I'm also have another one at -2. So I'm saying, this more or less looks like -2 to me. And now again, I'm still following this same behavior. It's just that when I get to these factors, I want to look at the degree of the factor. The degree of this factor here is 2. Since I don't see anything here, the degree of this factor is 1. Just like writing x, we don't write x raised to the first. So in this first one, at 0, so again, this factor right here gave me the 0, it's going to bounce. So here I'm going to get a bounce, whether it's going to be above or below. And let's get our ultimate end behavior going. So ultimately, I know it's going to go up to the left. Ultimate end behavior, I know it's going to go down to the right. When I get to this, the -2, this is my first degree. So I'm going to be passing through this one. I get to this one and I bounce because it was a second degree. And I continue back on like this. In terms of having you guys graph these, this is what I would want to see. I don't even care what these y values are, as long as you have it passes through here, it bounces right here, goes to -infinity to the right, and it goes to +infinity to the left. That's a perfect graph to me. Now, can you take these numbers and plug them into this formula and spit out a bunch of stuff? Yeah, I'm very confident you could. I care about that basically none. Just FYI. Does number 7 make sense?
Yeah.
Perfect.
Thank you.
Cool. My pleasure.
So just quickly, we don't need to know kind of like the slopes or anything of those in between parts?
Not at all. So I don't care about these values or these slopes. So in terms of slope, when we're talking about curves, it only is going to have like a slope, quote unquote, at a given point. And you guys don't know the calculus behind that yet. So I'm not really concerned with slopes, but in terms of like the actual graph itself, this is fine. If you drew your graph like this instead, and you did it in purple and it looked like that, I would still give that 100% credit. Again, I just want to see it going up to the left, passes through here at -2, bounces at 0, and then goes down to the right. Blue and purple would both be marked 100% correct, even though they clearly represent different values.
So for the other numbers, like the -3, -2, and so on, it would just keep bouncing to those points and then go down again?
Nope, so these are just saying plug in the points to get the actual graph. So if I wanted a nice graph for this, it would look like this. So let's go to, let's grab Desmos. So if I wanted a nice graph, which I personally don't care if it is nice or not, -3x to the third. It's -2 x squared, is that right? -3x to the third minus 6x squared. Close. So I'm going to zoom out just a little bit so you can see this thing. So we see it's going up to positive infinity as we go to the left. We see it's going down to negative infinity as we go to the right. I have a 0 here at -2, 0. I have a 0 here at 0, 0. And I see I pass through and then I bounce. That's all I'm looking for. But what this is saying is it's saying, okay, find what it's going to equal at -4, right? When x equals -4, this thing is going to equal, whatever big number this is. Look how far I have to zoom out. So, I don't even know where these things are intersecting. Right around here. So it looks like they intersect at -496. So if I were actually graphing this thing, that would be an actual point that I include. Again, I don't care about that. But as I go through, then I'd plug in -3, I'd plug in -2, to get all the points. That's what this is saying. But that's
You
the
want
part
all
that
the
I
points,
don't
but you
care.
don't want us to graph them all.
No, I don't care about the points at all. The only points that I care about are the zeros. So again, as long as it has the pass through here and the bounce here, I don't need you to graph a bunch of points. Like if you were to graph this thing, like an actual graph of this thing, you would have, a range from, roughly 150 to, -100 and something, just to capture from -4 to +4. And I don't care about that.
Okay.
So the only thing I'm caring about is this zoomed in version. Pass through here, bounce right here, call it a day. I don't need you to just plug in a bunch of points. So could you plug in -4 into this equation? Yeah. Could you plug in -3 into this equation? Yeah. But I'm not going to make you do that because that would take forever. We have to plug in 9 things.
Okay.
Yeah. Does that make sense?
Yeah.
Perfect. Any other questions on 7? Good to go. Switch up here. Now we're going to the chapter review number 15, I believe. Yep, chapter review number 15. So here we just want to find the real number solutions to the equation. So in this problem, it looks to me like my easiest route may be factor by grouping. I see these two things, and then I see these two things, and I think to myself, well, maybe there's something I can factor out here, and maybe there's something I can factor out here, so that they're the product of the same thing. So let's look at this. If I took out an x squared, this first one would turn into x plus 3. Now over here, if I took out a -1, I would have x plus 3. Now, since I'll write the -1 in here just so you can see it. So now I've got this times this chunk, and I have this times this chunk, and the chunks are the same, so I'm going to factor that out. So I'm going to factor out an x plus 3. When I factor out an x plus 3, what is left? X squared minus 1. So that's my factor by grouping. In terms of solving this, my next step would be to factor this a little bit further, or I could just set this thing equal to 0 as it is. So either way, whatever your personal preference is, I think I'd probably factor it one more just because it factors nicely into x plus 1, x minus 1. And then from here I solve. Here I get an x value of -3. Here I get an x value of -1. And here I get 1. So these are my 3 real solutions for this equation. Any questions on this one? Perfect. Perfect. Here we want to find the finite differences. So here we're just looking for nth order differences for the given function. So here we have a second degree function. So I know I'm going to be looking for second order differences. So for 23 here, basically I'm looking for second order. I want to plug a bunch of things in. So I want to plug in f of 1, f of 2, f of 3. Whoops, not a very good 3. F of 4, f of 5, and we'll do f of 6 and we'll call it good because I can't fit any more here.
Wait, so why are you doing all of those?
So this is how I show my finite order differences, is I grab evenly spaced x values. So my x values that I'm grabbing are just 1, 2, 3, 4, 5, 6, and I'm seeing what the y value spits out, and then I'll do the differences as I trace back. So like if I plugged a 1 into this equation, what would spit out? It'd be 1 minus 3 would give me -2. -2 plus 7 equals 5. So f of 1 equals 5. Does that make sense?
Yeah.
So I'm going to go do that for this entire thing. So I'm going to be doing x squared minus 3x plus 7. I'm going to go to my table here, and I'm going to grab my values. Let's see, I get 5, 5, 7, 11, 17, and 25. So I just put this into my calculator and made the calculator do the work for me. If you want to go through and evaluate each one of these, whatever floats your boat.
Mr. Goldenberg?
Yeah.
I'm going to go watch the video. I just don't want you to think I'm like ditching the Zoom.
Oh, no worries. You can leave whenever you're good. Thanks, Maggie. So now I'm doing 25 minus 17. So 25 minus 17 gives me 8. I'm going to do 17 minus 11, which will give me 6. 11 minus 7 gives me 4. 7 minus 5 gives me 2. And 5 minus 5 gives me 0. These are my first order differences, and I see that they are not all constant non-zero. So these are not all the same. So I'm going to go again. Because before we said we know we're going to go second order differences. So do it again. 8 minus 6 gives me 2. 6 minus 4, 2, 2, 2. So now I have shown I have second order differences here by showing that these are non-zero and constant. That's it. So in terms of like on a test, what I'd be looking for, that's all I'll be looking for, is that you like kind of show that work.
So there's no like actual specific answer besides like the work that's shown out?
The work shown out to just show the nth order differences is all this is looking for.
Okay, so if there was an answer, how you would just leave it at that?
So this whole thing, like if I were to put my answer in a box, it would be all of this stuff. That would be what I want to see for an answer. If I wanted the actual function, like if I was saying, okay, you start with this, find the function for me, like pretend I didn't give it to you here, then you would take 3 of the points because I know I'm a second order function. So I need 3 points to come up with the equation. And that's just all my matrix stuff. Do you want me to show you that? Or are you good on that?
Yeah, if you wouldn't mind.
Yeah, sure.
Thank you. Would that be on the test?
It would be, yep.
Okay.
So you should be able to do this to first find what degree it is. And then once you know the degree, you should be able to tell me the function. So in this instance here, we have a x squared plus bx plus c equals y. I don't know why that one didn't get capitalized. So this is my just standard form. So from here, I'm going to plug in the 3 points. So I'm going to grab these ones, because why not? Oops. So again, I'm just going to use these 3 points. You can use whatever 3 you want, it really doesn't matter. And now I'm going to be plugging each of these in. So each of these x's and then each of these y's. So this is the exact same thing we did before when we were doing like all the create an equation stuff. So I'll do this one in yellow. So I'll call this a times 1 squared plus b times 1 plus c equals 5. And then what does that turn into? It turns into a plus b plus c equals 5. Cool. Now the next one I'll do in blue. Now I'm doing for this one here. So I'd say a 2 squared plus b times 2 plus c equals 5. Turns into 4a plus 2b plus c equals 5. Do the next one in purple here. A times 3 squared plus b times 3 plus my c value equals 7. 9a plus 3b, whoops, not a great b, plus c equals 7. And now I'm going to take these 3 things and turn it into a matrix. So now my matrix for this thing is going to be a 3 by 4 matrix. And it would be 1, 1, 1, 5, 4, 2, 1, 5, 9, 3, 1, 7. And then I would go to my preferred matrix solver. So let's grab this one here. Use the TI-84 calculator, use Calculate 84, the app, whatever you want. Here I've got, again, a 3 by 4. In terms of my values here, let's see what we got. So we've got 1, 1, 1, 5. Then I got 4, 2, 1, 5. And then I got 9, 3, 1, 7. Yep, there we go. And then I'll just go down here to calculate. This again shows you all the steps, which are pretty cool, but I'm not going to have you do all the steps out, so I'm just going to skip to the bottom. Hopefully it doesn't crash. All the cool math syntax. Just got to load all these good ads first.
No, of course.
Free things like this have to support themselves somehow. Go buy your G-Shock watch now. Cool. All right. So now we get our reduced row echelon form matrix, which is swell. And so now, since that spit out this thing, my equation, as in my final answer, would look like y is equal to a single x squared minus 3x plus 7. And if we compare this to this, hey, we did it.
How did you take the matrix and get that equation from it?
The reduced row echelon form?
Oh, do you just take all of the, oh, yeah.
So this is my A value, so there's just one of them. Here's my B value, so that's where I'm getting -3 there. And then 7 is my C value. Does that help?
Yeah.
Cool. So yeah, so this is solving for A, B, and C. So now I'm saying, okay, the A value is 1, the B value is -3, and my C value is 7.
Okay, that makes sense.
Cool.
So what are you looking for in an answer? The A, B, C, or that Y equals that stuff?
The Y equals that stuff would be
Okay.
the final answer. And that's if I was asking you to come up with the equation. Just know that in a problem like this is what you'd be given. I wouldn't first give you this thing. You know what I mean?
Mhm.
So I would give
Okay.
you all these, then you would find out that it's second order differences. And then you'd use the knowledge that it's second order differences to set up your quadratic equation. So now that you've got this, A, B, C, you go through for 3 of the points, you get your matrix, reduced row echelon form, then you find your thing.
So
Wait,
if-
what did you say? Sorry, go ahead.
Can we go through it one more time? So like one version of this problem is just to show me this, right? So that's what this is asking you. It's saying show the nth order differences for this thing are non-zero and constant. So that's one version of this problem. Another version of this problem, instead of giving you this equation, I would say find it for me. Okay, so I wouldn't give you this. What I would give you is I would give you this string of points. I would give you 1, 5, 2, 5, 3, 7, 4, 11, 5, 17, 6, 25. And then I would say, find what equation gives me these points. And to do that, you would have to find what degree the equation is by taking your finite order differences. By doing that, you'd say, oh, I got all 2's on the second one, so they're my constant non-zero values, so this is a second degree. Once I know it's a second degree, I then start fitting it to a quadratic model. So this is my ax squared plus bx plus c equals y. This is different than, let's say, if it was a cubic model. If it was cubic, like it was third order differences, then I'd have ax cubed plus bx squared plus cx plus d equals y. So that's just an example of something else. That's cubic. This is quadratic, so this is second degree. So then I take 3 points, because I know that's all I need for a second degree equation, and I plug each of them in. I would get my 3 equations, I would put into a matrix. I would find reduced row echelon form of this matrix to solve for my A, B, C values, and I would just write my final equation.
So if it took us, if we didn't get to those all 2's in,
Oh, I think you're cutting out again, Emma. So Emma, I can't hear you, but I'm going to try and anticipate your question. If your question is, let's say these were not all 2's, you'd have to keep going until they are something, right? 5, 5, 5, 5, you know, whatever it may be.
So they all have to be the same number and then count how many times it took you to do that. And that's the degree?
That's the degree, yep. So see, here was the first one.
Yep.
And then this one's the second one. So since it worked on the second one, it means it's second order.
and then the amount of points you take from it is 1 more than the degree.
Correct, yep.
Okay.
And I'm probably unlikely to ask you to do anything more than a quadratic, just FYI. Just because it's a lot of work. Not that you couldn't do it. It's absolutely the same thing. You just do it one more time. It's just less likely, you know? What other questions you got?
I think I'm good.
Okay.
Okay, thank you.
My pleasure. See ya.
Bye.
Yeah, I think I'm all set too.
Alrighty. Have a good day.
You too.
Bye.